And again, we talked about really two big categories of reactions that pretty much account for all the reasons why chemical reactions take place. One big category, again, is our double displacement category. And again, in that category, it is a double exchange that's happening here between two ionic compounds, where our positive guys will switch partners here and make two new ionic compounds on the back end here. And again, if one of these guys does make a solid, that's what is referred to as a precipitate. And that is also more specifically classified as a precipitation reaction. Also, one of these guys can make water, and that's usually accompanied by an acid-base reaction. And again, this is usually a precipitation reaction. And those are really two of the three reasons why a reaction takes place. Is ultimately what's happening is you made water or you made a solid, and that's pretty much what took place in those reactions. The other big sort of category of reactions is redox reactions, and redox reactions are oxidation and reduction reactions that occur. And a reminder that oxidation and reduction always occurs together. So if there's something being oxidized, there should be something that is being reduced, and vice versa in that case. Several definitions of oxidation and reduction, but most of the time in general chemistry, we look at oxidation as really losing of electrons, while reduction is the gaining of electrons. And what that really entails in redox reactions is we have some electrons being transferred. And that basically is the third reason why chemical reactions take place, is those basically three reasons. Pretty much all of them boil down to either electrons being transferred, solid being made, or water being made. We also talked about a couple of things that you can easily, I guess I said easily there, easily determine what is being oxidized, what is being reduced by really following the, well, we'll talk about more today, the oxidation state of the elements from one side of the arrow to the other side. And as things lose electrons, they then have more protons than electrons, which means they become more positive. So if you see the oxidation state heading in this direction on the number line, sort of towards the positive side, that substance is going through oxidation. Vice versa of that is if somebody were to gain electrons, which is what happens when somebody goes through reduction, they then end up with more electrons than protons. And that means you'll see their oxidation number move in really the negative direction there on the number line, and it would be going through reduction here. We also talked about the oxidizing agents and the reducing agents. And the oxidizing agent is the substance that gets reduced, while the reducing agent is the substance that gets oxidized. And they are called the oxidation agent and reducing agent because, again, they cause really that opposite effect there, or that effect in the opposite substance. So again, if something is getting reduced, that means it's gaining electrons. The only way it could gain electrons is somebody has to lose electrons. So that is why it's known as the oxidizing agent, is causing the oxidation of the other substance. While obviously, if somebody's being oxidized, when it loses its electrons, somebody will have to gain those electrons, and it will cause a reduction in the other substance, which is why it's been known as the reducing agent. Both the substances being oxidized and reduced, and the oxidizing agent and the reducing agent, they're found on the reactant side there of the arrow, is typically where you find those guys. So in terms of redox reactions we'll talk about today, pretty much all other classification of reactions sort of fall under the redox umbrella, besides precipitation and acid and base reactions, which fall under the double displacement. As we might have talked about last time as well, in a double displacement reaction, there is no redox happening. So there's no electrons being transferred or anything like that. So on the guys over here on the left, no electrons being transferred. Over here on the right, pretty much all electrons are basically being transferred on this side. Any questions on any of that stuff there that we talked about last time? Okay. So I think we did this guy at the end there. So for example, here, if we look at the bottom one, which I think maybe we did not do, so we'll just kind of look at it real quick here. We have some copper wire here. And that's going to be solid copper reacting with a little silver nitrate in this case to form silver metal. And this is going to be a type of reaction, as we'll talk about, which is known as a single replacement reaction. And in a single replacement reaction, these are pretty much like those halogen type reactions that we did in that experiment way early on, where we had the different layers. This copper is going to come in, it's going to kick out the silver. And when the silver gets kicked out, it actually gets kicked out by itself. And the copper and the nitrate will come together and make a little copper 2 nitrate, perhaps. A little balancing like we're in chemistry class here. There we go. So this is a single replacement reaction. In this case, we want to know what is the oxidizing agent. This is again is a redox reaction that is happening. So if we look at the oxidation states here on the left-hand side of the arrow, remember that when anything is by itself, uncombined, it pretty much has 0 for its oxidation state or charge. When silver and nitrate are together, that's an ionic compound. So they have their normal sort of charges, if you will. That's a +1, and really the nitrate's -1. We could even go through nitrogen and oxygen, but we don't really need to. Silver on the right-hand side is no charge, as it is by itself. Copper over here is copper 2 nitrate, and that's a +2 and a -1 in this case. So when we look at what's happening here, once again, we could use our little number line action going on. And if we start with the copper started at 0, which is about there. And on the right-hand side, it actually ends at +2, which means it is moving in the positive direction. And since it's moving in the positive direction, that means that the copper here is actually going through oxidation. By default here, that would mean the silver here is actually going through reduction. And we know that also by going to the number line. Silver here is starting at +1 on the left-hand side, and it is ending at 0 on the right-hand side. They're becoming more negative. It is going through reduction. Any questions on that there? How about the nitrate? What's happening with that? Anything? Nothing. It's the same on both sides. So nitrate is not doing much in this case. In fact, it is a spectator ion. You could actually write a total ionic equation like we did with double displacement reactions here. Take the copper plus the 2 silver ions here, plus the 2 nitrates, goes to 2 of our silver here, and a copper with a +2, and 2 of the nitrates here. And as you can see, we actually have the nitrate is a spectator ion in this case. Leaves us really what is happening in this case, which is our net ionic equation, which is basically this reaction is taking place. Our net ionic equation, our total ionic equation, and obviously our molecular equation in this case, right? Or the metine and so forth. What is really happening here is an oxidation. It is an electron transfer. Electrons heading over there from the copper. Going to lay off 2 electrons, 1 to each of the silver ions, which is going to pick up the electrons and become silver with no charge on this side. And this guy will become positively charged on that side. What's essentially happening is, in this case, is you have copper, metal. You got silver ions floating around. Copper is going to lose some electrons and go for a swim. Silver is going to gain those electrons and basically come out of solution as a solid in that case. They're going to actually transfer electrons And that's what's going to happen in this particular case. So as you can see here, you can actually write a net ionic equation for a redox reaction like this, a single replacement reaction. And again, we have just the one spectator ion that's happening in this case. So to answer the question of what's being asked here, which is what is the oxidizing agent, and the thing that's the oxidizing agent is in this case, the oxidizing agent is the substance that is being reduced, which is the silver in this case, would be our oxidizing agent. Our reducing agent would actually be the solid copper in this case. So again, the agents are opposite of their name. So the oxidizing agent is the guy being reduced, and the reducing agent is the guy that's being oxidized. Any questions on that one there? I think that's right. All right. That's reassuring. There we go. So let's talk more about how we actually can identify oxidation numbers, which is obviously really important when you're doing redox reactions, and obviously like the study assignment when you got to balance some stuff. So let's talk about how we assign oxidation numbers, which are also sometimes referred to as oxidation states, whichever name you like better, I suppose. So the oxidation number is really the charge that the atom would have if all the electrons were actually completely transferred. So when we solve for oxidation numbers or oxidation states, they are sometimes different than what we associate with certain elements in the ionic sort of compound situation. So in an ionic compound situation, we do get the electrons to completely transfer from our metal to our non-metal. So they do gain those charges fully. So when we look at things like sulfur, you know, it's -2 in an ionic situation, or phosphorus is -3, chlorine is -1 when we have an ionic situation. And that's still the same case when we want to assign oxidation states for ionic compounds. Pretty much as you see here, one of those rules there is whatever their kind of charge in their ionic form is basically their oxidation state. Now, things are different when we look at even the same elements that we just talked about when they are covalently bonded together. And when they're covalently bonded, they are sharing electrons. So what happens in those situations is based on what they are attached to and how many they are attached to, it can have a big effect on their oxidation state. They actually can become, for example, more positive than we usually associate with it, and can be positive numbers because of the difference in electronegativity between that element and others. So for example here, anything though that is in their natural state that's uncombined will have an oxidation number of 0. So anything by itself, not combined, will definitely be 0. Monoatomic ions have oxidation numbers equal to their charges. So again, if you have something like iron 3 chloride, the iron is a +3 oxidation state, just like the charge would be. If it was like iron 3 chloride, the chloride would be -1, like we normally would associate with it in that situation. The oxidation number of oxygen is usually -2, which is usually a pretty good place to start. So if you have oxygen in there, that's a really good place to start with, which is -2. The only exception to that would be if it was peroxide. Like if you had hydrogen peroxide, then it would be -1. And again, that extra 2 you would kind of see hanging out there as well. So that would be -1 and +1 in terms of the hydrogen in this case. But probably 9 times out of 10, if you see oxygen, it probably is just oxygen, and it's going to have a -2 oxidation state. But again, if it happens to be something that's peroxide, then it would be -1. The oxidation number of hydrogen is +1 unless it comes after a metal, which makes it hydride, which is -1 like we talked about. Everybody in group 1 will still be +1. Everybody in group 2 is +2. Our friend fluorine is -1. When we do add up all of our oxidation numbers for everybody, it should equal the charge on the ion if it does have a charge, or if it's neutral, it should all add up to 0. The oxidation numbers do not have to be actually whole numbers. So for example, their superoxide is a -1/2 oxidation state. So if we look at something like HCO3 minus, for example. That is bicarbonate, I hope, or hydrogen carbonate in this case. When we want to assign the oxidation states for all the elements that are present, and you have something like this where oxygen is there, that is usually the best place to start. So I would start with the oxygen, which is -2. That gives me kind of like a -6 overall for all the oxygens that are present, since there's 3 of them. In a 3-pack like this, I would save the guy in the middle for the end and kind of go right, go left, and go to the middle at the end there. And that means if I go to the left there, that's going to be +1 for the hydrogen. The overall charge of this bicarbonate is -1, which means all of those guys do need to add up to -1. So that means that the oxidation state here of carbon should be +4, I believe. +1 and +4 is +5, and a -6 is a -1 left over. So when you are giving the answer here, the oxidation state for hydrogen should be +1. The oxidation state for carbon should be +4. The oxidation state for oxygen should be -2, not -6. So not the grand total. So when you're assigning oxidation numbers, it is just for one by itself. And you also should use the charges, yeah, not just the numbers. So you should write plus if it's a positive guy, and you should write negative if it's a negative oxidation state. First off, any questions on that there? So when I look at something like, say, chlorine, which we normally think about chlorine as being a -1, right? And that is definitely the case if you have something like sodium chloride. That's going to be a +1, -1 situation for the chlorine. And that is a metal and a non-metal together, where those electrons are being transferred from the metal over to the non-metal. But if you take chlorine, for example, in a situation like ClO3 minus, for example, that is chloride, I think they call that. Yeah. So that is going to give us a oxygen here with a -2 oxidation state, which gives us a -6. Overall charge here is going to be -1. That means in this case, the chlorine actually has a +5, yeah, oxidation state. And it has a +5 oxidation state in this case, and that gives me a grand total of -1 overall in our oxidation state. So why is it a plus versus the -1 that we always think about it in the case of chlorate? About drawing the perfect Lewis structure just to get the idea. Actually, I'll go down here. That way we're running out of screen, maybe. All right, so when we have, say, chlorine here with our oxygen, in this case, right, oxygen is probably going to be more electronegative than chlorine, which means the electrons that are being shared are going to head towards the oxygen, right? And they're going to be shared unequally, which means as those electrons move more and more towards the oxygens, the chlorine becomes more and more electron deficient, and they become more and more positively charged. Those electrons are not going to be completely transferred, but they're being sucked out closer to the outside, right, by the difference in electronegativity. So something that we normally think about, like chlorine, that's going to be a -1 charge when the electrons are completely transferred over to the chlorine. In the case where they're sharing electrons, in this case, chlorine is actually the one losing the battle there. It's actually having its electrons kind of moved away from it, and that's why it becomes more and more positive as well. So oxidation state or number is not always people have in their head at this point beat into their head the charges we think about for elements in an ionic compound sort of situation. But when we're dealing with things that are covalently bonded together, sharing of electrons, it's actually the difference in electronegativity that's going to make a big difference on particular element, especially if he's like in the middle and he's got more electronegative atoms on the outside, sucking the electrons away from it. It's actually going to become a more positive sort of oxidation state in that situation. Question on why it's positive and not negative in that case. I think that's right as well. So all right, so here's all these sort of oxidation states of everybody, so you should memorize them all. Not really, can't even see them probably, but that's Mn. It's got like a bunch of oxidation states. And again, here's our nitrogen, which we also think as negatively charged, or chlorine that has some positive ones. And again, we can definitely get some different sort of oxidation states versus the charges we normally associate. All right, with that being said, for each of these elements here, okay, let's take a look here. So we'll start at the bottom here. I'm going to start with the oxygen, which is always a good place to start. That's going to be a -2 or -2 there for our oxygen. Again, there's 3 of them, so that really does give us kind of a grand total of 6 if we take them all together. Going to the left-hand side there, that's sodium. So that's our group 1. It's going to definitely be +1. In this case, this has no charge, which equals 0. So in the case here, our I, to balance it out, has to be a +5 oxidation state. So our sodium here would be +1. Our I would be +5. And our oxygen, once again, would be -2 and not -6 in terms of the oxidation state. Any questions on any of those there? Coming to our IF7 here is fluorine, which is always -1. And that gives us basically a -7 happening. Overall, this thing is neutral, so it's 0. So in this case, the iodine actually needs to be +7 in this case, right, to balance it out. So it's +7. And that gives us an I that is +7. We have our fluorine that is -1. So once again, in this case, we basically have those really highly electronegative fluorines sucking the electrons towards itself, right? And it's making our iodine that we normally associate as a -1 charge in an ionic compound more and more electron deficient and more positive. So it takes on a +7 charge, as opposed to over here where it only had a +5 oxidation state because it was only hooked up to 3 oxygens in that case. Still some good bringing electrons towards the oxygens, but not as much obviously as that more electronegative fluorine that's going to bring those electrons towards itself. Lastly here, we got a little potassium dichromate. That's a -2 for the oxygens, a -14. The potassium there is +1, and there's 2 of them, gives you a +2. Overall, we got a 0 again. In this case, though, there are actually 2 of the chromiums, which means each chromium is going to be a +6 in that case, right? That gives us a +12, which gets us to 0. So potassium, once again, would have a +1 oxidation state. Chromium would be a +6. Again, not +12 total, just sort of effect there. Oxygen would still be -2 in this case. Question on any of those? That again is also why when we look at something, for example, like sulfate, right? And all of our oxygens are a -2 situation happening. And in this case, it is -2, -2, -2, -2. That is a -8 happening here. And sulfate has a -2 overall charge. So in this case, that's going to be a +6 action happening there with our sulfur in this case, where we normally think of sulfur in an ionic compound as being -2. Once again, sulfur and oxygen are in the same group on the periodic table. Oxygen is further up, which means it's more electronegative. So with sulfur being attached to these 4 oxygens, once again, going to kind of suck the electrons closer to each of those oxygens and making, again, sulfur in this particular arrangement more and more electron deficient and more positive in that particular case. And that's different than what you get when you got like sulfites, right, which is SO3 2-. I won't draw the correct Lewis structure here, but again, -2, -2, -2. That's a -6, which means it's only going to be a +4 in that situation. that last oxygen basically is not pulling as much, right? So it's going to have a little less of electrons moving out than it does with the extra oxygen there pulling it towards it. So still going to make it quite more electron deficient and more positive than it would be in an ionic compound, where the sulfur would actually be the receiving of the electrons. In this case, it's actually the one kind of giving away the electrons. And again, that's why it becomes more positive. Any questions on that? That's why it has to add up to -2 in that case. Yeah, so if we had and that's how we kind of get the charge as well. So if we had SO4 2 minus, we did it without the drawing there. This would be -2, which would give us -8. It does need to equal -2 overall. So in that case, we got a +6, right? And sort of where the -2 overall charge kind of comes from as well. Yeah. Any questions on that? And this is also why you might have wondered, you know, these are covalently bonded things, right? Why do they have charges, right? Why are they ions? And it has a lot to do with this. The guy in the middle is really kind of sucking those electrons out, that they gain these sort of partially charges, if you will, that overall allows them to have a net negative charge, even though they're sharing electrons and they're technically not transferring electrons. It's kind of like they're almost at that point of transferring, but they're still hanging on. So we get this really unequal sharing of electrons based on the elements that are present and why they are difference in electronegativity. Any questions on oxidation numbers? All right, I won't end that with I think, but I think that was right. All right, so here we're going to talk about now specific classifications of redox reactions. So just like we saw with double displacement reactions, that you can more specifically classify one of those reactions as either a precipitation reaction or a acid-base reaction. There's a whole list of more specific classifications of reactions that fall under the big umbrella of redox reactions. So the first one's a combination reaction. And in a combination reaction is also sometimes referred to as a synthesis reaction. It is definitely a redox reaction that's happening. But basically the way that you could recognize a synthesis or combination reactions is basically two things make one thing, basically. So two things come together to make one thing. Aluminum and bromine come together to make aluminum bromide. So that's two things make one thing. So you could classify this as a synthesis or combination reaction. It is still a redox reaction that is happening. If we look at the oxidation states of everybody, aluminum is by itself, which means it has an oxidation state of 0. That is the natural way that bromine comes, right? It comes as a diatomic molecule, which means it also has an oxidation state. Now here, though, we do have our metal and non-metal together. So that's going to make an ionic compound, which means these guys are going to have their normal sort of charges we think about. Aluminum will be +3, and the bromine there would be -1 in this case. And again, if you're not sure what is happening, we could go to our number line. Our aluminum is starting at 0 and ending at +3, which means it's definitely moving in the positive direction here, which means it is going through oxidation. If we look at the bromine, it started at 0 and it ends at -1, which is definitely going towards the negative direction, which means it is going through reduction in this case, right? So the aluminum here is being oxidized. The Br2 here is being reduced. And that means my reducing agent is which one? My reducing agent is the guy that gets oxidized. So that would be my aluminum. And this guy would be my oxidizing agent. So this is a redox reaction that's happening. Basically, electrons are being transferred, which is why this reaction takes place. And it could fall under the big classification of redox reactions, but most people probably that see this reaction would classify it more specifically as a synthesis or combination reaction. So again, there are multiple ways you can classify the same reaction depending on what you're looking at. Any questions on that there? The next sort of more specific classification of a redox reaction is pretty much the opposite of this reaction, which is known as a decomposition reaction. So in a decomposition reaction, we take one thing and we break it apart into a bunch of things. So Synthesis, we put it together, so two things make one. And decomposition, one thing makes multiple things. So it's kind of like the opposite of it. So one thing makes multiple things. So this is definitely a decomposition reaction. This, once again, is also still a redox reaction. If we look at the oxidation states of everybody here, oxygen on the left here is -2. Potassium there is going to be +1. And in this case, there are 3 oxygens, which makes it a -6. There's a +1, so it does equal 0, this molecule. And that means that the chlorine here is hanging out with a +5 situation. And that's because it's really attached to 3 oxygens, basically sucking out those electrons. On the right-hand side, that's actually an ionic compound, which means the potassium here is +1. The chlorine here is -1. And that is oxygen, how it naturally comes at the end there, which means it has an oxidation state of 0. So once again, if we look at what is happening here, we look at the we'll look at the chlorine. Chlorine is like +5 way over here. And on the left-hand side, the right-hand side, I'll get that. That is -1, which means it is moving in that direction. The chlorine here is actually becoming more negative and going through reduction. The oxygen here is -2, which is like over here. And on the right-hand side, it becomes 0, which means it's actually moving in the more positive direction, which means it is going through oxidation. Bless you. In this case, the potassium, is anything happening with potassium? There is nothing happening with potassium. It's actually just a spectator ion, basically, right? It's kind of the same on both sides. It is really, in this case, it is the chlorine here that is being reduced. And it is the oxygen here that is being oxidized in this particular case. Any questions on that? So here we could clearly demonstrate through oxidation states that it is a redox reaction. We have electrons being transferred. Once again, the electrons here are actually being transferred from the oxygen to the chlorine in this case. And the chlorine is receiving those electrons, which is why it's being reduced. So decomposition, both a redox reaction, reason it's happening is those electrons are being transferred. More specifically, once again, probably most people would classify that as a decomposition reaction rather than a redox reaction, even though it is still a redox reaction and it's happening. Any question on those two there? It is. So this is potassium chlorate, which is actually kind of the one I sketched, I think, on the other page without the potassium. But the polyatomic is basically this guy, yeah? And this is our polyatomic ion, which has an overall -1 charge, right? And again, these guys are all sharing electrons here. And those oxygens are going to suck out those electrons closer to them, making the chlorine, in that case, have that positive charge. And the oxygen here actually will, like I said, lose some of the electrons as it kind of breaks apart. And at that point, it's going to be the chlorine that picks them up over here. And that's why it ends up as a negative charge as it picks up those electrons that are being transferred. So through this process of heating this, we're obviously going to break some of those bonds within the polyatomic ion, right? And it's going to kind of configure into KCl, and O2 is going to be generated. So a couple of these oxygens are going to hook up to make the O2, and then that C and O bond is going to break and allow the chlorine to attach to kind of the potassium, just kind of hanging out there as well. Yeah. Any other questions on that? Okay. Yeah. The coefficients have no effect on the oxidation states. So when you want to assign oxidation states, you want to just take it kind of like just the formula itself. So kind of similar to when you do like molar mass or something like that. When you try to calculate the molar mass of a compound, you just want to take the formula itself, regardless of the coefficient that might be in the balance equation. It'll have no effect on it. Same thing with the oxidation state. Because that's why really, again, we're assigning it really for the individual elements that are in that formula of what each of those individual elements are. And so that coefficient will have no effect on it. Other questions? Okay. There that is. The next type of reaction is a combustion reaction, and there's really kind of two types of combustion reactions, and I would say probably 99.5% of the people, I don't know, I made that number up there, but 99.5% of the people, if you tell them, hey, tell me a combustion reaction, this is probably not the reactions that we see up here, the ones they were thinking of. Most people, when you think about a combustion reaction, is a combustion reaction where you take some type of organic compound that usually contains carbon, hydrogen, and oxygen, kind of like what we talked about with our combustion analysis when we did our empirical formulas, right? Plus some oxygen, makes a little CO2 and water. Like when you light your Bunsen burner, you have some methane, right? And you get some oxygen, some CO2 and water, and basically you usually get a flame and some heat associated with a combustion reaction. Propane, butane, those are all organic compounds, which obviously are flammable and typically go through a combustion reaction. So I would say most people, when they talk about combustion, think about the organic combustion, which is this one. And really the main components of the organic combustion is there's O2, and you always kind of get CO2 and water is usually the products that are produced, unless you get an incomplete combustion, which means you get carbon monoxide and water, but most of the time it should be CO2 and water. Now, really, in order for something to be considered a combustion reaction, there's really just a basic definition of, frankly, that's all you need to see right there, is you just need to see oxygen there on the left-hand side of the arrow, and you could call that one a combustion reaction. Congratulations, it's good. So if you have something that has oxygen involved, it's technically a combustion reaction, but again, I would say probably almost 99% of the time, people think about the organic combustion as the combustion reaction. So here we definitely have some oxygen involved in each of these reactions, which would classify them as a combustion reaction. No surprise, probably at this point, this is still a redox reaction, both of these things. If we look at the sulfur here, that's naturally how it comes, that's a 0. That's also naturally how it comes, so that's going to be a 0 oxidation state. Oxygen here is going to be -2. There's 2 of them, which gives you a -4. So the sulfur in this case will be probably a +4 if I did my math better there. That'd be a +4 right there. So in this case, the sulfur has +4. And once again, if we sort of follow what's happening here, our sulfur is starting at 0 and ending at +4, which means it is becoming more positive. So it is the sulfur here that's going through oxidation. The oxygen is starting at 0 and ending at -2, which is becoming more negative and going through reduction. So in this case, that guy is going through oxidation. That guy is going through reduction. That means that is my reducing agent. That is my oxidizing agent, right? So that is definitely a redox reaction that's happening. It's definitely a combustion reaction because it has oxygen. It's also what other type of reaction? I see 2 things that make one thing. That's also a synthesis or combination reaction, right? So you technically classify that reaction one of 3 ways. It could be classified as a redox reaction because there's definitely electrons being happening here. It is a combustion reaction because it meets the basic definition of there's oxygen involved. And it also has 2 things coming together to make one thing, which is a synthesis or combination reaction. So this one reaction could be classified 3 different ways. I would just choose the best classification depending on the situation of whatever question you're answering. Same thing down here. We got oxygen. We have also redox, 0 and 0. This is going to be +2 and -2. And again, here it is our magnesium that's becoming more positive, going from 0 to +2. And that's going to be oxidized. And this guy here is being reduced. So it definitely is a redox reaction. And by the way, when you have a reaction like this, where you have a metal and a non-metal, the one that should always be oxidized is always going to be the metal, right? And the non-metal should always be the one that's going to be reduced in that case. So that is a combustion reaction. That is a redox reaction. That also is a 2 things make one, synthesis combination reaction. So there you go, multiple ways to classify the same reaction. Any questions on either of those there? By the way, if you've done this one before, you burned the magnesium ribbon, You're supposed to observe what happens without looking directly at it. Otherwise, you won't be able to see for a while. The last sort of type of redox sort of reaction that falls under the redox umbrella is really single replacement reactions or displacement reactions, depending on whose book you're reading this with. But these are our single replacement reactions. And again, how you can recognize the difference between this and a double displacement reaction, which is not a redox reaction, is you will have this general setup to start with. You definitely will have an ionic compound happening. And you will have one element by itself, which may be a metal. And if it is a metal, it actually will have no oxidation state, as it'll be by itself, right? Being by themselves from the periodic table, have no charges, no oxidation state. But when a metal does get a charge, it normally is what type of charge? Positive or negative? It is a positive one, which means when it comes in, it will kick out the positive ion. That way that it will then gain a charge, and you will make a new ionic compound. And that guy that it replaced will come out with basically no charge. And it cannot bind with the positive guy there, because then you would have two positives, which won't work, right? So the electrons here are actually being lost by A coming in and being gained by the metal that has the charge there, which is B in this case, and it gets reduced. You could also do this just like that experiment we did with a non-metal, that one where we had the different layers. We're in the fume hood looking for changes in the upper layer there. And in this case, the non-metal would not have a charge to begin with because it's by itself. But when non-metals do have charges, they are negative, which means it will come in and kick out the negative guy in this case. And once again, it will make a new ionic compound, and that guy coming in will then gain a charge of negative, and the guy coming out will actually have no charge in that particular case. If you remember when we talked about those reactions and did that experiment, in order for A to come in, it has to be more or less reactive than what it's trying to replace. It needs to be more reactive than what it's trying to replace, right? So A in this case, for this reaction to take place, needs to be more reactive than what it is replacing. So big category reactions, these are all redox reactions that are happening. More specific classification is single replacement reactions. And you can even go a step further and classify it more and more specifically by the type of displacement that's happening there. So this is what is sometimes referred to as a hydrogen displacement, because the metal here is coming in and kicking out hydrogen. Fancy name, but still a single replacement reaction. Whenever you kick out hydrogen from its ionic form, it becomes hydrogen gas. Those are all the bubbles you see as you do this reaction. This is what is sometimes more specifically referred to as a metal displacement. So again, we can recognize this as no charge. You could think of the hydrogen here as +1, oxygen is -2. And here, this is plus minus and no charge. So metal gonna kick out the metal. So that's why sometimes it's referred to as a metal displacement. And here's our halogen, where the halogen will kick out the halogen in this case, 0, +1, and -1. These are all still redox reactions. So once again, if we look at the bottom one here, +1, -1, and 0. In this case, for the bottom one, the chlorine is starting at 0 and ending at -1, which means it is becoming more negative, is being reduced. The bromine here is actually starting at -1, which would be like here, and ending at 0, which means it is being oxidized in this particular case. That means what is essentially happening here is the chlorine is actually gaining some electrons in this particular case. And the bromine there, bromide, is losing some electrons and becoming more positive in this case. So the electrons are actually, believe it or not, going from that guy to that guy in that particular case. Any questions on that there? Yeah. Now, again, as we talked about, in certain cases, these reactions will happen. In other cases, they will not happen. And again, they will not happen if whatever is coming in is less reactive than what is trying to replace. There's what's sometimes referred to as an activity series. And I think in that experiment, you kind of made one where you kind of put all the elements in order based on the reactivity. But a basic, this is a really fancy activity series with more specific information. But a basic activity series is really just a list of elements. You know, like, for example, got hydrogen usually in the middle. And when you look at an activity series, usually anything higher on the list will replace anybody lower on the list, and anybody lower on the list will not replace anybody higher on the list. So that's why when you take something like zinc and some hydrochloric acid, this reaction will take place because zinc is more reactive than hydrogen, will produce your hydrogen gas and your zinc chloride. And maybe a 2 there. But if you try to do the same reaction there with copper, it will not work. It will get no reaction as copper is less reactive than hydrogen in this case, right? So if you take a new penny and you file it open, what's inside a new penny? What element? Zinc's actually inside the new penny, and the outside is copper. Yeah. So if you file it open, it used to be an experiment we used to do years ago, but you would take 2 pennies, one's an old penny, one's a new penny, right? New penny, you'd file some holes in it. New penny, you would file holes in it as well. Old penny is made up of pure copper inside and out. So you throw your old penny into HCl, penny's still there. Throw your new penny into the HCl, the outside of the penny's there, the inside's gone because the zinc will react with the hydrochloric acid because you filed holes in it and allowed the acid to reach it. Was a cool experiment until they said, well, we probably shouldn't be filing and money and stuff like that and using it for labs. So this one's more specific here. So we can see on the list, calcium plus water, definitely water reactive. All you need is basically cold water to have that one react. And that's a lot of our group 1 and group 2 metals, which are very water reactive. Throw potassium in water, catches on fire and all that kind of stuff. Very, very reactive. But if you try to deal with lead, lead is not going to work. Water is not going to be strong enough. You do need an actual acid to make that sort of occur. So that bottom reaction would not occur if you try to do it with lead and water. But if you put lead in some acid, you would have some reaction that would occur. So any questions on that there? We also, from that experiment, actually determined this. And as you remember, hopefully your activity series for the halogens is group 7 on the periodic table, right? And reactivity increases as you go up. And that's what we saw, right? We saw that the chlorine replaced the bromine and the iodine when we did that experiment. We saw that the bromine replaced the iodine, but not the chlorine. And we saw the iodine didn't do nothing, basically, but stayed purple at that part. So, and then obviously we didn't do fluorine, but fluorine is more reactive than all of them. So here we would expect these to happen. Once again, these are still redox reactions. So we would expect this one to happen as chlorine is higher up in the group there than bromine. This one we would not expect to occur again because the iodine is less reactive than the bromine, so it will not take place. Lastly here, it is possible that the same element can be both oxidized and reduced at the same time in the same reaction. Is sometimes referred to as a disproportionation reaction. Happens a lot with chlorine. And if we look at this particular reaction here, we look at the chlorine on the left there, that is a 0 oxidation state. We have the oxygen here, which is -2, hydrogen is +1. And over here, our oxygen is -2 and +1 for the chlorine on that guy to get us to -1 overall charge. That's -1 for our chloride ion that's floating around. And that's a -2 and a +1 happening there. So if we look at the oxygen, the hydrogen, not much happening on either side. It's actually the chlorine here. First thing's happening is the chlorine is going to make this guy. And then that same chlorine, by the way, will then make that guy in that case. And this is actually the two things that's happening. They are both starting at 0. and the chlorine over here is going to be +1 and then -1 in this case. So in the top reaction, when we look at the chlorine, starts at 0, ends at +1, so it is becoming oxidized in this reaction. When we look at the chlorine in the second reaction, starting at 0, ending at -1, so it is becoming reduced. So that chlorine is both being oxidized and reduced, and the two half reactions would have the same reactant, yeah, and then two different products, right, in each of those guys. Any questions on disproportionation reaction there? All right, so lastly here, in terms of classifying reactions, we could look at some of these here. This is acid-base reaction, kind of the net ionic equation here happening. This is our single replacement reaction, which is also a redox reaction. This is our synthesis, which is also a redox reaction, right? This would be a double displacement reaction. And we have our calcium carbonate, which is going to be our precipitation reaction, which is also a double displacement reaction as well. So again, you can classify reactions in multiple ways depending on what you're looking at. And again, you want to choose sort of the best selection. So to summarize all the different reactions that we talked about and ways to classify them, once again, under the big double displacement umbrella, where there is no electrons being transferred, no redox happening, that is more specific classifications of precipitation and acid-base reactions. Under the redox reactions, which are all about electrons being transferred, we have our synthesis, combination, more specific classification. We have our decomposition, which is our more specific classification. We have our single replacement reaction, and we have our combustion reaction. So once again, as we talked about many times, this is our electron transfer. That is our solid being made, and that is our water being made. And once again, that is the 1, 2, 3 reasons why a reaction takes place, and they fall under basically those two big categories, which you can then classify more specifically. Any questions on reactions, way to classify reactions, redox reactions? Okay, so that wraps up this little bit here. We are going to actually, since we're in the redox mood of redox reactions, so we're going to talk about how to balance these redox reactions in a more complicated situation, like you'll find in that study assignment, like you'll also find in the lab tonight as well, some of the post-lab questions. So let's talk about that. So obviously we have our basics from what we just talked about. Obviously now we know how to identify oxidation numbers, which is really important in balancing these guys. So in a basic redox reaction, you know, if we had something like our magnesium plus our oxygen and our magnesium oxide, we can write our half reactions, which in this case would be magnesium will lose a couple of electrons, plus 2 electrons here. And we do need to make sure, obviously, we have the same number of electrons. So that sometimes it requires you to multiply one of the half reactions by a common number, or maybe both half reactions in certain cases. You know, for example, if you had a 3 and a 2, right, the common number there would be 6. So you would have to multiply both half reactions. In this case, we just need to multiply the top one by 2. And that would get me my 4 electrons, right, that I need. And now I can add these back together. What should always happen, because this is a redox reaction, is the electrons should always completely cancel out, because the idea of a redox reaction is however many electrons somebody loses should be the exact same number of electrons somebody gains. So they should always cancel out. You could also think of the arrow as like an equal sign, like in math, right? So they kind of cancel each other out. Anything that's on opposite sides of the arrows in different reactions or even the same reaction can cancel down or reduce down as well. I think that's the only thing that's going to cancel here. And then everybody on the left-hand side of the arrow will stay there. So that is 2 magnesiums plus an oxygen on the right-hand side of the arrow. I basically have 2 of these ions here. And I got 2 of these ions here. And since these are ions, they're actually going to come together to make just 2 of the magnesium oxides in this case. And these are actually solids. All right. Or they're aqueous and they will make a solid at the end. So that will give us our overall reaction here of what is going on. All right, so from that really butchered example there, basically in a basic redox situation, if you have the 2 half reactions, the one thing you want to make sure before you add back together the half reactions is you want to make sure you always have the same number of electrons in each half reaction. Questions on that there? All right, so let's talk a little bit about how we balance redox reactions in either acidic conditions or basic conditions, which is a little bit more involved. So if it is acidic or basic conditions that we want to balance these in, there are several steps that you have to follow. So the first thing you want to do is split your reaction into the half reactions. You want to split your overall reaction into the 2 half reactions. One should be an oxidation half reaction and one should be a reduction half reaction. Once you have split it off into half reactions, you want to balance all the elements except for hydrogen and oxygen. So you want to balance all the other elements just like you normally would using coefficients for all the other elements except for hydrogen and oxygen. And you want to do that for each half reaction, whichever one might need it. Once you have done that, you then want to balance the oxygens by adding water to the side that needs the oxygen. Now, when we add water, we're adding water to balance out the oxygens. But when I add water, I'm not just adding oxygen to that side, I'm also adding hydrogen, right? So because of that, and because we don't want to be short hydrogens at the end of the day, to the opposite side, you need to add 2 H pluses for every water you added. So one side, you're going to add a certain number of waters to balance out the oxygens that you need. And then to the other side from where you added the water, the other side of the arrow, whichever side that may be, you need to add 2 H pluses for every water that you added. That will make sure that at the end you are not short hydrogens. By the way, if you are starting out in a half reaction where you have more hydrogen on one side than the other, then you could add just H pluses to the other side. So if you happen to be starting out at some point with a half reaction where you got like, and it's like, oh, and you're short like a hydrogen, you could just add an H plus to the other side to balance it out. At some point, you'll need to do that. So you could just do it up front if you're unbalanced in terms of the hydrogen to begin with, for sure that you can see it. All right, once you've added the water, once you've added your H pluses, you are now ready to balance the overall charge on each side of the arrow by adding electrons. So because electrons are negatively charged, you need to add it to whichever side needs the negative charge. Now, when we're talking about equal overall charge, which I highly recommend, that's what you look at. Some people are taught, like, look at each element and try to figure out what's going on. You're wasting your time to do that because the overall charge of everything is already given to you, which takes into the account everybody's individual oxidation states. So just look at everybody's overall charge. And that means that it does not need to be 0 and 0 on both sides. It could be. It just needs to be the same number on both sides. So if you got like a +2 on the left, you need to get to a +2 on the right. You know, if you got like, you know, a -3 on the left, you need a -3 on the right, or maybe 0 and 0 on both sides. So sometimes people think you got to get it to 0 and 0 overall charge on each side. You don't. It just needs to be the exact same number on each side. And you're going to add the electrons to whichever side does that. Once you've done that, you want to make sure you have the same number of electrons in each half reaction. And if you do not, then obviously you might need to multiply by a common number like we did in the previous example. So if not, multiply. And once you have the same number of electrons on each half reaction, add them together. And again, here, the electrons should always completely cancel out. Questions on those steps? That's a lot of steps. Let's do one together and see how we put all these steps together. All right, so this is basically the steps that I put here is how you would balance one of these redox reactions in acidic conditions. And I will show you at the end how to turn it into a basic at the end of those steps. So let's take a look at one here together. So let's say we wanted to first balance this in acidic conditions, and we got this guy going on right here. The first thing we want to do is split it off into its half reactions. So really the easiest thing to do is just find the two things, one on each side that has the same elements in it. So clearly here I got iron on that side, and I got me some iron over here. So those two things go together. And the other guy has chromate or chromium in it. So I got this guy and this guy here. Yeah. So these are our two half reactions. It's also a really good idea to figure out which one's your oxidation and which one's your reduction, because it could help you make sure you're not screwing up the process later on. So we're going to do that by our oxidation numbers. So we know that iron here is +2. We just did this guy in the example, and that chromium was +6, and that oxygen was -2. The iron here is +3, and that is a chromium with a +3 charge. So in this case, the iron is being oxidized or reduced. The iron is going from +2, which is here, to +3, which is in that direction, right? Which means it is being oxidized. By default, the chromium here is going to be reduced. We could also see that by chromium starting at +6 and ending at +3, which means it is moving in a more negative direction, right? So same rules there. All right, so really the top half reaction there is our oxidation half reaction. The bottom one there is our reduction half reaction. I need a nap by this point. But here we're going to balance everything other than oxygen and hydrogen. And in the case of the top reaction there, I got one iron on each side. I'm not looking at the charges, just the actual coefficients of how many are there, or subscripts. On the second one, though, I got two chromiums on the left, and I got only one chromium on the right. So I do need to balance that. So again, we're just going to balance it like normal and put a 2. Questions up to that point there. All right, now I balance everything but oxygen and hydrogen. Now I should attack oxygen. There is no oxygen in the first reaction, so that's good. In the second reaction, there is 7 oxygens on the left and none on the right, which means I do need to add water to the second reaction. I should add 7 waters to which side? The right-hand side has no oxygen, so I'm going to lay me up there 7 waters on the right-hand side. Since I put 7 waters on the right-hand side, I just added 14 hydrogens to that side, which means to the left-hand side, I need to add 14 H pluses. So that's important. They're not H2s or anything like that. They're H pluses as well. Yeah. Any questions on that? So that's what we were talking about there in the instructions. Water to one side, 2 H pluses for every water to the other side. That's going to keep your hydrogens nice and balanced when it's all said and done. All right, so I've clearly here have added my waters, I've added my hydrogens. Now I am ready to balance the overall charge on each side. So this is how you should do it. We'll start with the top one. Overall charge on this side is a +2, right? Because there's just an iron 2 on that side. Overall charge on the right-hand side is +3. Could only add a negatively charged electrons. Which one should need the electrons, right or left? Right-hand side needs a grand total of 1 electron. That's going to give me a -1 to go with my +3, which gives me a +2 now on the right to match the +2 that's on the left. So this is also what I was talking about earlier. It does not need to be 0 on both sides, just needs to be the same number on both sides. And now I got a +2 and a +2. I'm happy there. You're happy, I'm happy, everybody's happy. Let's go to the bottom here. And here again, I'm not going to overcomplicate my life because what I know about oxidation numbers is what? When I add them all together, they should equal the overall charge on the actual formula, right? So when I look at this, which has an overall charge of -2, I don't need to go individual for everybody. I know it's going to add up to -2, right? So no sense going individual, wasting your time. I got 14 +1s here, which gives me a +14 happening there. 14 and -2 gives me a grand total of a +12 on the left-hand side. Right-hand side, I have 2 times +3, which is +6, and water is 0, right? So basically I got a +6 on the right, a +12 on the left. Which side needs the electrons? The left-hand side, right? And we will need 6 electrons in this case. 6 electrons gives me a -6, which gives me a +6 on the left to mask my +6 I got going on the right-hand side. Any questions on that there? So again, I would highly recommend just taking the overall charge because it frankly does all the math for you. Why do the math again? You know, so why go like chromium lost like 6 electrons or gained 6 or whatever? It does it for you. You don't need to do it. Any questions on that there? I'm going to rewrite everything underneath because I got a lot of scribbling going on here. So we got Fe 2 plus goes to Fe 3 plus and an electron. I got me 6 electrons plus 14 of these guys plus this goes to this and that. How do I know I added the electrons to the right side or the correct side? Top half reaction is the oxidation half reaction, right? Which means electrons should end up on reactant or product side. Should end up on the product side like they're being given off. So that's a way you could check yourself, and why you should also figure out which one's being oxidized, which one's being reduced. Bottom one's the reduction half reaction, which means electrons should end up on the reactant side, which they did. So that's a good way to check yourself. Either if you get the wrong answer there, either you added the electrons to the wrong side, or you didn't correctly identify what's being oxidized or what's being reduced. So it should always match up that way. All that's left here is I want to add this back together. But before I could add it back together, I need to make sure the electrons are the same number in each, which they are not in this case, right? That means the top guy, which I'll come up here, needs to be multiplied by 6. Yeah, everybody in the top guy needs to be multiplied by 6. That's going to give me a 6 there, a 6 there, and a 6 if I squeeze it in right about there. Now I can add this back together. Anything on opposite sides of the arrow should cancel out. Electrons should completely cancel out as they are on opposite sides of the arrow. And I frankly think that is all of the canceling we're going to see at this point. 14 H pluses plus some Cr2O7 2 minus plus our 6 iron 2 goes to our 6 iron 3 plus our 2 Cr3 plus and our 7 waters in this case. Now, if I did everything correctly, I could put a box around it. I could put a happy face. I could put that it is balanced in acidic conditions. But how do I know it really is balanced in acidic conditions? Well, I feel like we didn't make too much of a mistake here, but we should probably check it this way. If it is properly balanced, it needs to actually be balanced 2 ways. The first way is like a normal balanced equation, which means you should have the same number of elements on each side. So if we look, I got 14 H's, I got 14 H's. I got 2 Cr's, I got 2 Cr's. I got 7 oxygens, I got 7 oxygens. I got me 6 irons, and I got me 6 irons. So it is balanced like a normal chemical equation. The other way that it should always be balanced is overall charge on each side should be exactly the same. So if we look at the overall charge, my H pluses gives me a plus 14. This guy is going to give me a minus 2 overall. This is going to give me a plus 12. That is going to give me some bad math there, but that's going to give me 26 less 2 is like a plus 24 happening there on the left-hand side. On the right-hand side, I got a plus 18 happening from the iron. 6 times 3. 2 times 3 is plus 6, and that is going to give me a 0. I hope that's plus 24. No, that is. Look at that. So it is plus 24 on both sides, balanced overall charge, balanced the number of elements on both sides. This would be balanced in acidic conditions. Any questions on any of those steps there? All right. Now to show you how to turn it into basic, my recommendation is there's multiple ways to do it. My recommendation is to do it just like this, balance it as it's acidic, and then at the end, you could actually just turn it into basic at the end, which is a much easier way to do it. So if you had to balance this in basic conditions, you're going to do everything just like we just did. You're going to now take your acidic formula, and I'm just going to erase the top there just to rewrite our guy at the bottom there, I think. Maybe I'm going to erase the top here. That guy, there you go. Okay, so if we needed to turn this into basic, you could turn it into basic pretty quickly by just taking your acidic equation. And when we go to turn it into basic, what we want to do is we're going to add OH minus to both sides. And it's going to be equal to the number of H pluses you have. So when you look at your acidically balanced equation, you have a certain number of H pluses, which in this case is 14 in our example, right? You're going to add 14 OH minuses to both sides. So I'm going to do that. I'm just going to recopy the guy on the bottom and add my 14 OH minuses to both sides. So on the left-hand side there, we would have 14 OH minuses plus our 14 H pluses plus our Cr2O7 2 minus plus our 6 iron 2 goes to our 6 of the iron 3 plus our 2 of the Cr3 2 plus our 7 waters and our 14 OH minuses, once again added not to just one side but both sides. Yeah. Now the side where you have H plus and OH minus, what do you get when you put together H plus and OH minus? It becomes water. Yeah, so H plus and OH minus will become water. So that will give us 14 waters on the left-hand side. I now have 7 waters on the right-hand side and 14 on the left. That means water 7s get subtracted over here, and that leaves me a net of 7 waters on the left, plus my Cr2O72 minus, plus my 6 of the iron 2, to my 6 of the iron 3, my 2 of the chromium, and my 14 OH minuses. And if I did that correctly right there, I put another happy face and I call that balanced in basic conditions. It should still be balanced both ways. So once again, 14 hydrogens on each side. 7 and 7 is 14 oxygens, 7 in each of those, 14 oxygens. 6 irons, 2 chromiums, 2 chromiums. Overall charge on the left is -2 and +12, which gives us a +10, I think, if I got that right. Overall here is a +18, a +6, which is a +24, and a -14. That is a +10. It is still balanced in each way. Yeah, so we have the same number of elements, the same charge on each side. That is probably the easiest way to turn it into basic, is to just balance it in acidic and convert it at the end. You could actually do it in the middle where you add before you add the electrons, but it's a lot more like canceling stuff out, and you definitely don't want to do that. To finish up here, I know that the top one here is balanced in basic conditions because I see what in it? OH minus, which is a base. And the bottom one's balanced in acidic conditions because I see H plus in that format, which means it's acidic. Yeah, so that's how you know which one's which. Cares. Good time. Let's take a break. Let's go to the lab at some point. Yes.